Today, we'll have a look at the fundamentals of hardware design with Silice, a programming language for FPGAs I have been working on. There are no prerequisites apart from basic knowledge of programming languages. After today, you'll have a better understanding of the basic principles behind Silice and FPGA programming. You'll be able to write a simple LED blinker in Silice and to start exploring the many example projects. But for now, let's have a look at what's inside an FPGA. An FPGA is a grid of similar logic cell elements. These basic elements are surrounded by a network of electrical traces. The traces can be connected at their intersections, and this of course is configurable. Each logic cell is in fact a small lookup table, a small memory that you can configure to describe what should be the output of the cell given its inputs. This lets you emulate any logical gate such as XOR, OR, AND, or NAND. By connecting these elementary cells together, you can describe any digital circuit you want. And of course, these connections are made at the intersections of the network of electrical traces surrounding the cells. Programs written in Silice are compiled into a configuration for the logical elements and interconnections of an FPGA. Silice is far from alone in achieving this goal. In fact, a full open source software stack is used. The output of Silice is fed into a software called Yosys, and then NextPNR, to create the final configuration file for the FPGA. It's worth noting that the output of Silice is a Verilog program, a very common hardware description language. Silice can import Verilog modules, and Silice code can be reused from Verilog. So, how do we program an FPGA? We're going to start from the clock signal that gets inside the FPGA, and in particular focus on one clock cycle. At every cycle, our hardware design will take inputs, apply some computations to them through circuits, and produce outputs. These typically will be the inputs to the next clock cycle. Here is an example program in Silice. Let's see how this translates in computations per clock cycles. Here is our clock signal. On the first cycle, this blue block will be active. On the second cycle, this brown block is active. The reason this line was split to a different cycle is because the programmer used the step operator. Next, we have a loop, and the block inside the loop will be active every cycle after that, for a number of times depending on the value of b. As you can see, the syntax itself shows us how the computations will map to clock cycles. And this is a very important concept of Silice. In particular, Silice never implicitly introduces steps. You have full control of how the cycles are being used by your hardware. The rules are precise, and all defined in the documentation for typical flow constructs: if-else, while, subroutines, and others. Now, let's see how these computations at every clock cycle are turned into circuits. Here, we have a simple block that takes A, B, and C as inputs and produces new values for them. This is turned into this circuit. A, for instance, is a set of wires, maybe 8 if it is an 8-bit variable. Each wire is a bit of A and will have a voltage of ground if the bit is 0, or VCC if the bit is 1. And this truly is how it happens inside the FPGA. Each operation here, such as the +1 box, corresponds to a set of logic cells combined together to update the values of the wires with the corresponding operation. In this case, adding 1. The == 0 box is a multiplexer that selects the new value of B based on the value of C. Interestingly, you can see that regardless of C, both outcomes generate a circuit. There is no notion of not computing something here. Everything is always active. Now, looking at this, and knowing these are actual electric wires, you may wonder how we are not producing a closed-loop circuit. Well, without an additional component, we actually are. And this is not good, as the electrical signals will become unstable and desynchronized in these loops. To make this work, we need another very important ingredient from FPGA circuits, and these are flip-flops. The flip-flop acts as a barrier between the old value and the new value output by the circuit. Here is how. On the left, the clock signal. The arrow represents time. Initially, the flip-flop outputs 0, all wires to ground. This can be configured. Then, the electric signals go through the wires, reach the gates, and on the other side, the electric signals in the wire represents the value +1. This propagates until the flip-flop, where it is stopped. Nothing else happens, the circuit is now stable. On the next positive edge of the clock signal, the flip-flop copies the values from its input to its output. This makes the circuit unstable again, and the signal propagates through the wires and gates until it reaches the input of the flip-flop. At this point, the circuit is again stable. Note that there remains plenty of time before the next positive edge. As you can guess, if the circuit is not stable when the next positive edge comes, we are in trouble. This will drive the frequency at which our hardware can operate. In the end, what this means is that Silis internally holds two views of each variable: its Q value from the previous cycle and its D value being updated during the current cycle. Most often, Silis deals with this, but there are cases where you have to manipulate both. Let's go back to our little circuit here. What happens if the signal takes too long to propagate within a cycle? Well, you can use the step operator to split the circuit in two. Now these competitions will take 2 cycles, but the circuit at each step is less deep. Hopefully it is obvious by now that there is a trade-off between how much you can do during the cycle and what maximum frequency you can reach. There is no obvious better choice here, as it really depends on your design goals, and Silis gives you full control over this. Now let's talk about a difficulty that is known as combinational cycles. Let's consider this piece of Silis code. The first part is fine and will become this circuit. The second part reuses the value of A, which has just been updated. This again results in a loop in the circuit. The problem here is that Silis generates a single flip-flop for A, so it cannot deal with the second update. Silis will issue an error. How can we fix that? The first approach is to split in 2 cycles as suggested by the error message. We could also rewrite the code in nested if-else conditions, but that results in a more complex circuit. The third way is to introduce a temporary variable, TMP. Which one is better? Well, that again depends, which is why Silis lets you in charge. So to recap, we have seen how code becomes circuits. We have seen that shorter circuits means higher frequency, and that longer circuits means more work done at each cycle. Now let's talk about parallelism. When I showed you this, it was slightly misleading, because in fact, both circuits coexist in the FPGA. They take the same inputs. Their outputs are selected by a multiplexer. This together implements a finite state machine that Silis automatically generates for you. Now, let us take a more global point of view. The state machine takes flip-flops as inputs, perform computations in parallel circuits, which outputs are selected by the multiplexer based on the active block index. The result is then fed back to the flip-flops. This implements an algorithm. Of course, you can run another same algorithm in parallel, or a different one. All of these would be active together inside the FPGA. Other constructs, such as pipelines, are also possible. So how do we do that with Silis? Every design has a main algorithm. In a way, this is the entry point of the design. The main algorithm always becomes a circuit. Here we have implemented Blinky, the hello world of FPGAs, where we simply blink LEDs. Note the bit select syntax that here selects 8 bits from bit 16 and assigns them to the output that drives the LEDs. We can also declare other algorithms. Here we define the increment algorithm. We then instantiate the algorithm in main. We can then call the algorithm with a list of inputs and outputs. This here is a synchronized call, which blocks until the called algorithm is done. So an algorithm declaration defines a blueprint that we then instantiate in other algorithms. Each instance becomes an independent circuit. Main does not need to be instanced. This is done automatically. So how do we run things in parallel? Well, that's easy. Here is an example. We define the wait a second algorithm that, well, waits for a second. Then we instance it in main and call it, but this time with a non-blocking call. Main just keeps going and does stuff. Let's assume this takes less than a second. When done, main joins with the wait a second algorithm. It simply waits until this other algorithm is done. Alright, a few more notes. We can run many algorithms in parallel. This is of course the whole point. Algorithms can also auto-run, so they run as background tasks. For instance, doing I/O such as driving video signals or updating a game world. Algorithm inputs and outputs can be accessed while they run. Algorithm instances can be connected together through bindings, forming larger designs. So that's great, but there's a but. Space is limited on the FPGA, both for logic cells and routing. And that means you'll hit some limits in design size, or routing capability, or low frequency due to long routing delays. But hey, where's the fun without a good challenge? So I hope you've enjoyed this video. Next time we'll discover more of the Silice syntax. Until next time, please have fun coding with Silice. Be sure to check out the many example projects. See you soon!